the invitation. It's thanks to all of you for coming. So in my first lecture, I mentioned a few results, but not much proofs. So today, this is the second lecture. There will be another one after this. I want to present two different methods for proving large-scale regularities in elliptic homogenization. The same approach can also be applied to parabolic equation systems, where you not only have oscillation in space variable, but also oscillation in time variable. Okay, so here my intention is to present the idea in a very simple setting, and also mention a few extensions here. So today, I will describe the compactness method, and this is a classical method in the study of nonlinear PDEs and the calculus of variation. Nevertheless, even though we're dealing with linear equation here, it's still it's a very powerful tool. Okay, so let me first recall that the operator for the elliptic equation we're dealing with is in divergence form. And there is a parameter, small parameter epsilon in the coefficient matrix, and it appeared in the denominator of the variable. So my operator depends on epsilon, written in the form of minus divergence of A of x over epsilon times the gradient. Okay, and you can write this out in components, in indices here. So both I and j are summed from 1 to d, d being the dimension of the space. So here, let's just look at the matrix, rescale the matrix A of y, no epsilon here. So the basic assumptions are that A is real, bounded measurable, and uniformly elliptic. Although similar approach can also be carried out with complex coefficients, maybe in more general setting here. But we also need a structure condition. So here we're going to assuming that A is periodic. Periodic with respect to some integer lattice. After a change of variable, you can also you can always assume it's periodic with respect to the standard lattice ZD, and we call such function one periodic. One periodic means that periodic with respect to the integer lattice. Right? So so ellipticity means that the matrix is positive definite. Ellipticity constant is denoted by mu, which is positive, and we're also assuming the matrix is bounded. You can always choose a constant, so the upper bound is mu to the power -1. Okay, and periodicity means that, as I already described, it's periodic, one periodic with respect to integer lattice. That is, just if you add a point with integer coordinates, it's the same. A of y plus z is A of y for any z and for almost every y here. Okay. We also in the presentation, I'm also always assuming it's a scalar for simplicity, but the same result, same proof works for second order elliptic systems in divergence form. Please feel free to stop me anytime for questions, please. All right, so the uniform regularity we want to study here is that suppose you look at an equation, elliptic equation, L epsilon U epsilon equal to F, you can assume F is independent of epsilon. It doesn't matter because F here is fixed. The solution depends on epsilon, so it's denoted by epsilon. So what we want to know is that for which space this solution belongs to uniformly in epsilon. Epsilon, say, is between 0 and 1 here. All right, so I already present this example that if you look at the function xk, that's just the case components of the variable x, plus epsilon times chi k of x over epsilon. Chi k here is the so-called corrector. It's a periodic function. Periodic function, and which can be obtained by solving a boundary value. I mean, a elliptic equation or system on torus, meaning that you're solving a boundary value problem with periodic boundary conditions. Okay, so then this function is a solution in the whole space. So that gives you some idea what kind of regularity to be expected. So we take the gradient of U epsilon. We got a gradient of xk, which is a constant. And then you have, take the gradient of second term, there will be an epsilon -1 come out, cancel out. You got a gradient of chi k of x over epsilon, okay? So that's second term is only bounded as far as the continuity is concerned. It's not even uniformly continuous in epsilon. And therefore, as far as the regularity, uniform regularity, the best estimate we can hope for is Lipschitz. Lipschitz meaning that the solution is uniformly the gradient of the solution is uniformly bounded. We cannot expect C1 alpha estimate. Although I mentioned C1 alpha large scale, but that has to be interpreted by subtracting the appropriate correctors. So there is a large scale C1 alpha, even CK alpha estimate if you're introducing higher order correctors. But here we're just looking at the solution itself without worry about correctors. So the solution is only uniformly elliptic, uniformly Lipschitz. Okay, so this is a.
Can I ask a question?
Yes, please.
Previous slide, please.
Yes.
Any requirement for the omega, domain omega?
Omega, yes, there will be conditions on omega if you want uniform estimate up to the boundary. Yes. So in the next theorem, there will be a condition. We need to assuming omega to be C1 alpha.
Also, that omega is much bigger than the reference cell.
Yeah. Epsilon is assumed to be small because
Okay.
if epsilon is away from 0, then everything is classical.
Okay, thank you.
Whenever you differentiate, the epsilon come up in the denominator. If epsilon stay away from 0, then there's no problem at all. Thank you. So this is a classical theorem due to Marco Avellaneda and Fenghua Lin back in '87. And they prove the Lipschitz estimate up to the boundary for the Dirichlet condition. So here I write this out in terms of a system. In that case, you have a tensor. Aij alpha beta, which is uniformly elliptic, periodic, and also Hilbert continuous. Okay, and omega, as you asked, has to be C1 alpha. Actually, you cannot expect Lipschitz estimate even for C1 domains, which is simply not true, even for harmonic functions. There's no Lipschitz estimate for harmonics functions on C1 domains. So you look at this elliptic equation in omega with Dirichlet boundary conditions, U epsilon equal to F on the boundary of omega. So the estimate is that if P is greater than the dimension D and sigma is positive, so I'm assuming F is in C1 sigma. And then the L infinity norm of the gradient of the solution, this is the Lipschitz norm, is uniformly bounded by the data, LP norm of F, capital F, plus C1 sigma norm of the boundary data, little f. So the most important thing in the theorem is that this constant C is independent of the parameter. And if you allow C to depend on epsilon, then this is well known in classical PDE textbook here. This theorem is more or less optimal in several aspects. First of all, I already mentioned the domain has to be C1 alpha, not true for C1. P has to be greater than the dimension. It's not true for P equal to the dimension. Sigma has to be positive. It's not true for sigma equal to 0. And we know this already even for Laplace equation in a classical setting. Okay, so and I'm going to describe the proof of this theorem, but mostly on the interior part. And I'll say what needs to be done to get a boundary estimate. The boundary actually is much harder than the interior. But so I will present the interior estimate in some detail, give you some idea, and then I'll say the steps are needed to prove boundary estimate. Okay, any questions, please?
Yes, you mentioned about the sharpness of P sigma. How about the Hilbert continuous for the coefficient Aij?
Hilbert continuous, it's I think it can be relaxed, but to what extent I don't know. But it's not true. I don't believe it's true for continuous functions.
Right.
Yeah. Maybe some kind of Dini conditions would work.
Yeah. Thank you.
So the smoothness condition of the coefficient is only used for small scale, the scale below epsilon. It's not for large scale. We do not need any conditions, just bounded measurable would work. So anytime you have a local estimate, you can couple with a large scale to relax the condition on A. Yeah. Okay, so it takes some time to actually prove the Lipschitz estimate for the Neumann condition. So here is a theorem I did with Carlos Koenig and Fenghua Lim about more than 10 years ago. So there are two papers. The second paper I had with Scott Armstrong extend the first paper in two different directions. First of all, it used a different method, which is the method by convergence rate, which I'm going to discuss in the next lecture. And secondly, the method actually can be extended to non-periodic case, particular to coefficients which are quasi-periodic or almost periodic in some sense. Okay, so I'll talk more about that next time. In any case, this is about the Neumann problem. So the equation is the same: L epsilon U epsilon equal to F in omega. But instead of the Dirichlet condition, we impose the Neumann boundary condition. So the Neumann boundary condition is variational. So the conormal derivative is du epsilon d nu epsilon is the conormal derivative associated with the operator. So I don't have this write down. It just is the definition of that is just the normal dot with the flux of dot with a of x over epsilon times the gradient of epsilon. So that's just the variation form. When you, in other words, it's just the boundary data when you integrate by parts obtained from the equation here. Okay, so the estimate is similar. So we can have uniform bound for the Lipschitz norm in terms of the data. F is still in LP, P greater than the dimension. But since the Neumann data is imposed on the derivative, so the G here actually is in C sigma, but sigma has to be positive. Again, the most important thing here is that the constant C is independent of epsilon. Okay, so again, the sigma need to be positive. It's not true even for harmonic functions. You have Lipschitz estimate for continuous data for Neumann problem. All right, questions? Okay, so I will be spend most of the time on the proof of this theorem, which referred to as the large-scale interior Lipschitz estimate. Okay, so here you look at a matrix which is elliptic, periodic, no other smoothness conditions, just bounded measurable would work. So we have a solution in a ball of radius 1, can always scale to radius 1. For simplicity, I'm just take the right-hand side to be 0. You can also have a external force F in the right-hand side, but the estimate will take a different form. But it's the method is exactly the same. So this is consider a very simple case. So you have a solution in a unit ball. The estimate is that if I take R between 1 and epsilon, so little r has to be greater or equal to epsilon, and you take the average, that integral, put a slash in the middle, meaning the average, the integral divided by the volume, by the measure of the BR. Of the square of the gradient is controlled by a constant times the average of square of the gradient over B1. Okay, so roughly just meaning that the L2 average of the gradient of the solution on a ball BR is controlled by the L2 average of the gradient of the solution on a ball B1. And R here has to be between epsilon and 1. And C is depends only on the dimension and the ellipticity constant mu. Okay, again, I emphasize that no smoothness assumption on the coefficient A is needed, but we do need to assuming that A is periodic, or one periodic in this case here. Okay. So this is referred as a large scale, large meaning that R is greater or equal to epsilon. Epsilon is the microscopic scale here. Anything below epsilon is referred as a small scale. Okay. So I'm going to talk about the proof of this theorem, the compactness method. So that's interior. It doesn't deal with boundary here. All right. So first, let's see how do we combine this large scale estimate with the classical theorem for small scale to get a full scale interior Lipschitz estimate. Okay, so let's say you have matrix A, which is elliptic, periodic as before, but now we're also assuming that A is Hilbert continuous. Satisfy this condition. A of x minus A of y, absolute value is bounded by x minus y to the power lambda. Lambda is some number between 0 and 1. Okay, so you have a solution in B1 in a unit ball, and this time, instead of average, I can control the value of the gradient of u epsilon at 0 at the center of the ball by the L2 average of the ball of the gradient over B1. Okay, so this is mostly likely you saw from PDE book. You always deal with harmonic function first, and this is of course is true for harmonic functions. And now the point is that this is extended to equations, elliptic equations appear in homogenization theory here. Again, the C here depend only on dimension, ellipticity, and these two parameters, lambda and m, in the smoothness condition. Okay, so how do we prove this full scale using large scale and small scale? How do we combine? Actually, the proof is that it's quite easy. All right, so first of all, we notice that if epsilon stay away from 0, then everything is classical, because the Hilbert continuity of A of x over epsilon will be uniform, because epsilon appear on the denominator. So if epsilon is great, for instance, greater or equal to 1/2, there's no problem at all. So you do have this estimate. Okay, so next we're going to do a rescaling. So we consider the function epsilon to the -1, u epsilon of x. U epsilon is the solution. So we rescale the variable x to epsilon x. Okay, and then this function v will satisfy the equation L1 of v equal to 0. And this rescaling property will be used in the compactness. It's very important in the compactness argument. Okay, so L1 of v, well, that's just a classical elliptic equation or system. We know we have the Lipschitz estimate, assuming the coefficient is Hilbert continuous. Okay, so the gradient of v at 0 is bounded by the L2 average of the gradient over the ball B1. Now let's scale this estimate back to u epsilon. So what you see here is that if I take the gradient of v and that epsilon to the -1 just cancel out. It's just equal to the gradient of u epsilon evaluate at epsilon x. So in particular, if I take x to be 0, the gradient of v at 0 is the same as gradient of u epsilon at 0. And so the first inequality in the last line there, last display there, is the same as the previous inequality when you change variable on both sides. I mean, the left-hand side is the same. When you do a change of variable, and then the integral over B1 of the gradient of V becomes the integral of gradient of U epsilon over B epsilon. So that's, so far I have not used any homogenization. Just everything classical here. We have not used the periodicity of the coefficient here. The large scale estimate is used in the second inequality, that red inequality. That is because, so going back here, I'm sorry, the large estimate, the lowest we can go is R equal to epsilon. And we just use that inequality with R equal to epsilon. The average over B epsilon is controlled by the L2 average over B1. So everything combined together give you that the gradient U epsilon evaluated at center is controlled by the L2 average over B1.
So the previous was gradient estimated by gradient, whereas this is the gradient estimated by U. So
very good. So I should put a gradient there.
Okay.
But you can also get away with the Caccioppoli.
Okay. Okay. In that case, I mean, I was just curious. Oh yes, you can get away with that one because epsilon is way smaller than 1. Okay. Yeah.
Yes. Yes. I should put a gradient there just to be consistent. Yeah. But from gradient to U epsilon, you can choose Caccioppoli and go back and forth.
So where's the compactness arrive? Is it in the large scale estimates?
No, the compactness is used in the proof of the large scale estimate. We haven't used that yet.
Also, I want to make sure I understand correctly. So these gradients, also because the gradient on the U, X, and the gradient on the V, they're all with respect to X.
Yes, yes.
Okay.
Yeah, epsilon is fixed. Yeah. All right. So let's talk about the compactness. How do we prove the large scale estimate? So to talk about the compactness, we have to first talk about the compactness of solutions within some class. Okay, so here I will put all the D by D periodic matrix together in a set, and I call that set M of mu. Mu is the elliptic constant. So they can have a different matrix, but they all share the same ellipticity constant with mu. So I put them together. Okay. Then the theorem say that I'm going to consider a sequence of solutions which are also allow the matrix to change in this class of M of mu. So I'm doing compactness not just for one fixed matrix, but for all matrix in the same class. It's the class of matrix periodic with the same ellipticity constant mu. Okay, so epsilon k goes to 0, and A super k belongs to this class of matrices. Okay, so suppose that this U sub k is bounded in H1 of omega. Omega here only need to be Lipschitz, I think, with no smoothness. Okay, required. Then there's a subsequence which I still denote by U sub k, such that U sub k converges to U0 weakly in H1. This is trivial because we know we have a weak compactness in H1. Any bounded sequence has a subsequence which converge weakly in H1. That's not a problem. The key here is that the limit of this subsequence U0, the limit U0 of this subsequence is a solution to a elliptic equation in divergence form with constant coefficients. A super zero here. A super zero is a constant and a positive definite matrix. So this is the compactness theorem we're going to use in order to prove the large scale estimate I talked about earlier. Questions?
Yes, a question. So does A0 necessarily have the same ellipticity?
Very good.
Condition.
So A0 in general, the lower bound is the same. The upper bound may be different, but the
Okay.
upper bound depends on mu. And
Yeah.
So we cannot guarantee that A0 will be in the same M.
Right. There's no like point-wise convergence or anything like that that would immediately guarantee the same bound.
Yeah, no.
Okay. All right. Thanks.
All right, thank you. So how do we prove this? Well, here is an argument here. So first of all, because we have a weak compactness in H1, we can always assuming there's a subsequence which converge weakly in H1. We'll still denote the subsequence by mu sub k. So that's okay. The second step, we look at the homogenized matrix of AK, which is denoted by AK hat. In my last lecture, I defined the homogenized or the effective matrix for any periodic matrix. Okay, so the idea is that this AK hat may be different for each K, but they're all bounded. And therefore, by compactness, you can assume the subsequence also converge. This is just converge in each entry in the space, Euclidean space D by D. Okay. And A0 satisfy the same lower bound, but the upper bound depend on the dimension and also mu. Okay. And the last step is to use something called a Dirichlet lemma or Tatar's test function method to show that you also have a flux convergence weakly in L2. So I don't have time to show you this. So basically, what is the Dirichlet lemma? Dirichlet lemma is used to deal with the following situation. So you have two sequences which converge weakly. In general, if the product of two weakly converging sequences may not converge weakly. If you one strong, one weak, you do have strong is even better, but weak is not good. So the so-called Dirichlet lemma saying that if this product have some structure, special structure, you can still have some kind of weak convergence from the product. The structure you have there is one of them is in the gradient form, another is in the gradient form. Therefore, the curve is zero, and another has in the curve has some condition, and then you multiply, then the product will converge. So this is also kind of related to so-called compensated compactness, but this is a much simpler setting. Okay, and there's also a classical approach called look Tatar's test function, and you can choose some special test function and then use that in a weak formulation of the PDE to do so. So this will take advantage of the periodic structure, and you do that because it's periodic, and there you have some correctors which which can be used. All right, so now let's just showing how do we carry out this compactness argument using this compactness theorem. Okay, and so this is something called a two-step or three steps argument. the idea is that you use compactness to gain a little bit of regularity in the first step. And then you iterate to repeat this gain to this, eventually you reach down to the small scale epsilon. Okay, so so the setup may be a little, if you this is the first time you see this, it may be a little complicated, but take a while to be able to appreciate this. So we fix a parameter sigma between 0 and 1. And then there exist two other parameters, epsilon 0 between 0 and 1/2, and the theta between 0 and 1/4, which only depend on the dimension, ellipticity, and sigma, such that whenever you have a solution in B1, whenever epsilon is between 0 and epsilon 0, then you have this estimate, this inequality. That is the average over B theta, U epsilon minus its average, then minus this term which involved the corrector chi there. So chi is the corrector associated with L epsilon. And there's also a linear function. And then multiply by the gradient. And then you square it, integrate average over B sigma. This is bounded by sigma to the power 2 plus 2 sigma. 2 is important there. Sigma is the one I fixed in the first place, times the average of U epsilon square over B1. Okay, so in a classical setting, you do not see corrector. What you try to measure here is that you try to measure the regularity. How do you measure regularity? One thing that we do in PDE is that you measure the regularity by measure the distance between the function and the linear function, right? So the linear function here, if you think the corrector is not there, the thing I'm subtract there, the first term is a constant, and the second term is just the x times the average of the gradient, which is the constant here. So you try to measure the regularity by measure the distance between the function and the linear function. The smaller the better here. And here, when it turns out that the setting here, you don't have to do this in maximum norm. Actually, it's better to do the L2 norm because you're going to take the limit. And so what's going on here is that if you go down from ball B1 to ball B sigma, you gain sigma squared plus 2 sigma, theta to the power 2 plus 2 sigma, which is much small, which is small because sigma is less than 1. That's just, this is called a one-step improvement.
Can I ask the question here? So here's, this is only true for some theta, right? Not any small theta. Is it the statement like that?
Say it again, I'm sorry.
Here theta is only some theta.
Yes, yes. So this theta is just some number between 0 and 1/4. That's right. Yeah. So that's why it's called a one step. We just go from 1 to theta. In the second lemma, we're going to have to keep doing this from theta to theta squared to theta squared, theta cubed, and you simply iterate the gain you obtain from this lemma. So that's the this one-step improvement. All right. So the proof is done by contradiction. Compactness basically is a contradiction. So you take a theta to be determined in the last step. So you're assuming there's no epsilon 0 exists for this theta. Okay. And then there will be 3 sequences. First, you have a sequence of epsilon k goes to 0. Then you have a sequence solution, u sub k. And then you have a sequence matrix, A super K, belongs to that class of matrices. Satisfy the equation in B1, you normalize the L2 norm on B1 to B1, and this average on B theta, you got a reversed inequality. So it's greater or equal to theta squared plus 2 sigma. You simply reverse this inequality. Okay. And here chi k is the corrector for A super K. You can also do this for a single matrix, but then your constant will depend on the matrix. You do not have uniform control. So it's better to do this argument in a whole class of matrices. So your constant only depend on the ellipticity. Okay. So now we're going to do find a contradiction. So first of all, by Katropoli, we know the sequence is uniformly bounded in H1, B1 half. And therefore, we can assuming it's weakly converge in H1, B1 half, because we can also assume it strongly converge, weakly converge in L2, B1, because L2 norm is uniformly bounded on B1. We can also assuming by passing to a subsequence, the homogenized matrix of AK converge to A0 because they are constant, they are bounded, subsequence converge. They just constant converge. And then you take the limit in the inequalities. Okay, so assuming U sub K is bounded, and so you can apply the Fatou's lemma. So the limit will have L2 norm bounded by 1. And in this inequality here, you can take the limit. You see, U sub K converge strongly in L2 because it weakly converge in H1. So the first term converge, the average converge, the gradient, the average of the gradient also converge because you have a weak convergence. And then the other term, because their sigma epsilon K converge to 0, that bring that term away. And what you only left is this inequality. The corrector is gone because the corrector has a coefficient epsilon K. And here is the place to find a contradiction. So again, by the compactness theorem, the limit is a solution of elliptic equation with constant coefficients, and which we know a lot about the regularity. Okay, so we can use the C2 regularity for the elliptic system with constant coefficients. Okay, so the first inequality is the one I have in the previous page. That's obtained by taking the limit on the both sides of that inequality. The second inequality is just some calculus. You can look at this just more or less just the Taylor expansion. If you subtract the constant term, the linear term, and you can control by the second derivative. The third inequality is the regularity for the elliptic equation with constant coefficients. The L2 derivative is controlled by the average of the solution. So you have a sigma to the power 4 there. And then we know that the L2 average on B1 half is bounded because the average on B1 is already bounded. So you have a C0. All right. So now what you do here is look at both sides. In the left-hand side, I have a power 2 plus 2 sigma. Sigma is less than 1. On the right-hand side, I have a power 4. So what you need to do is that you choose a theta so small that it violates this inequality. Because when theta is small, the right-hand side goes to 0 in the power 4, the other will be less than 4. The choice of theta, because all the constants here depend only on the ellipticity or dimension. So the choice, theta only need to depend on the dimension and the ellipticity. And that's the proof of the first lemma.
Question.
Yes.
Could you go back to the previous slides? Yeah.
Yeah.
So this is, if I remember correctly, you introduced V differently earlier. This V has nothing to do with the previous V.
No. This V is not a rescaled limit.
Okay, I see.
Yeah, sorry about that.
Okay,
So,
that's okay.
yeah. So this V is just the limit of UK or a
Okay, just a
subsequent
limit.
of UK.
Okay.
Yeah, that's right.
Okay.
Yeah. So this V has nothing to do with that V. So this V is just the limit of a subsequent of U sub K.
Yeah, I have a question. So,
Yes.
for your theorem, so your sigma is on the power term, right? So it's a little bit different than other estimates. So, did you find maybe I think do you find some relationship between these two integral looks like ex or log x some function? Then you get some such estimate.
Not sure what do you.
I mean here the sigma is on the power term, right?
Yeah, sigma is just some parameter. I choose between 0 and 1. Can be as close to 1 as possible.
My question is why it comes out to be the power term to the exponent. So.
Why is the power here in terms?
Power.
You try to measure this is more related to kind of a C1 alpha estimate.
C1 alpha estimate.
Yeah, that's right. So you see here in the proof, we use the C2 regularity for equations with constant coefficients. When you do the compactness argument, you always lose a little bit. So from C2, for the limiting function, we have C1 alpha for the sequence. That's actually the essence of the compactness.
Okay.
So the essence of compactness is that if the limit is very good, the sequence cannot be very bad, cannot be too bad. And so that's kind of reverse what we do in analysis course. If the sequence is good, then the limit is good. Now we try to argue other way. But we're saying that if the limit is good, the sequence cannot be too bad. That's what's this part.
6.
All right. So the second step is iteration. So what you do here is that for the from the first lemma, we go from scale 1 to scale theta. And if you do this again, you go from theta to theta squared. You keep doing this as long as you can. You eventually reach down to the scale epsilon. So this is the statement here. I have a solution where the epsilon is much smaller than theta. Epsilon is less than epsilon 0 times theta to the k minus 1. K is some integer. Okay, and then we can show that if I measure the distance between the solution and a constant and times a linear function plus the corrector, and this is bounded by theta to the power 2 plus 2 sigma times k times the L1 average of U epsilon squared. Okay, and moreover, I have the control on this constant HK written in this form. Okay, so this is first of all, this is done by induction. The base case k equal to 1, it's just in the last lemma. That's the first case here, and then you prove this by induction. Suppose it's true for k, and then what do? You rescale the solution. You subtract a constant, subtract this guy here. The key observation is that this function v, which is a different v. I'm sorry, I keep using v. This is not the same v we're talking about before. So it's a different v now. Is a solution of an equation L epsilon over theta to the power k. So this family of operators have a very nice scaling structure. When I scale the solution, it appeared you just simply scale the parameter epsilon. So it's a solution of the same operator, but with a different parameter. The parameter changed to epsilon over theta to the k. But this new parameter satisfies the same condition as in the first lemma. So we can apply the estimate in the first lemma for this function v. Okay, and so the first inequality is by the last lemma, and the second inequality is by induction assumption. You assume it's true for k and try to prove for k plus 1. And then you just change this back to, scale this back to u epsilon, and you got exactly what you wanted. Okay, so the second step is just a rescaling technique. That's not much. Okay, yeah.
Can I ask another question?
Yeah.
So can you explain a little bit more what the significance of the coefficients HK are?
Yes, because it's going to be clear in the next slides. Because when I estimate in this here, so let's just finish the proof here.
All
so
right.
you assuming you have a solution in B1 and you have a R between epsilon and 1. You can assume R is already less or equal to epsilon 0 theta, because if R is greater, then it's classical. And then you can choose a parameter k, an integer k, so R is sitting between these two powers of a theta, between k and k plus 1.
Right.
Yeah, so then you estimate the L2 norm, L2 average, and then first of all, you do Katropoli, reduce to the integral of u epsilon minus some constant, this constant E sub k, okay? That's just a Katropoli for elliptic equation or systems. E k there can be any constant there. And then you subtract that linear function plus the corrector. And so you, by triangle, you have a second term. So the second term, you have a h of k. And so we need the estimate on h of k to have a bound for the second term. Maybe that answers your question.
Yes. That's the piece I was looking for to get the picture there. Thank you.
Yeah. So not only you want to have control on the difference between the solution and the linear function plus corrector, you also need to have a control on the hk. That h of k behaves like a tangent, kind of a slope for the tangent plane of tangent. Yeah. So we need some control on the hk, so it sum up to the bound of B1 there. Right. So that's the proof. I'll give you some idea of flavor of what's involved here. So this is for the interior estimate. So there is a C1 alpha estimate. This is called a large scale C1 alpha estimate. So you have to, instead of subtract a linear function, you have to add this corrector into the formulation. Otherwise, you do not get C1 alpha. That's why you don't get a classical C1 alpha estimate. Yeah. All right. So if I have non-zero right-hand side f, and this is the interior estimate. Okay. So the L2 L infinity norm of the gradient of the solution on a ball of radius r/2 is controlled by L2 average of the solution divided by 1 over r, divided by r, and plus r times the LP average of f. This is just all this r here. It's just a scaling factor there. So that's the interior Lipschitz estimate. Okay. So what about boundary? What do you do with the boundary? The boundary is, so the theorem was for the Dirichlet problem. This was approved by Avellaneda and Lin. So if we want to carry this machinery to the boundary estimate, we need to find a new corrector, which we call the Dirichlet corrector. The reason is that when we do this, you can still do the first lemma with the interior corrector chi. The problem is with the scaling, the second lemma, the iteration. When we iterate this, if we use the corrector chi k, everything mess up on the boundary. It does not satisfy the right boundary condition. So in other words, if you don't correct the boundary, the error introduced by this corrector chi k builds up on the boundary, eventually blows up the argument. So the right thing to do here is to introducing something called a Dirichlet corrector, which is a solution to the equation with right-hand side 0 and take the linear function as the boundary data. Okay, so imagine if your coefficient is a constant, then the linear function is just a solution, and therefore this. But if you have a general variable coefficients, the linear function is not a solution. So it's you have to do something else there. So this Dirichlet corrector replace the corrector in the compactness argument. And once we have, so the key estimate is to prove the Dirichlet corrector satisfy the Lipschitz estimate first, before you prove the general Lipschitz estimate for general solutions. So this is the key lemma in their paper there. And so this is quite complicated. There are several steps. First, you use compactness to do the boundary Hilder, and then you introducing the Green's function, and then from step 1, you can do the Hilder estimate for the Green's function, and then you prove some large-scale estimate on a boundary for a boundary data of spectral type, say in theorem in the step 3, and then you can do iteration. Then you can prove this lemma, and then you can do this compactness in this particular form. Okay, so in the place of the corrector, we have to replace the linear function plus epsilon chi k by this Dirichlet corrector phi epsilon. And so that's what we do. So that's mostly. That's why it takes many years to figure out this the Lipschitz estimate for the Neumann problem. So this is the Neumann problem I mentioned earlier. Again, it's the key step to using this compactness machinery is to introduce the so-called Neumann corrector. So what is the Neumann corrector? So the Neumann corrector is a solution in omega. Its Neumann data is the Neumann data of its DD nu 0 of the linear function chi k. And DD nu 0 is the conormal derivative for the homogenized operator. And so, the key lemma here is to prove this Neumann corrector satisfy the Lipschitz estimate uniformly in epsilon, and it use several estimates over there. Okay, so that's all I want to say. Thank you very much.
All right, so maybe let's thank this Professor Shen again one more time.
Thank you.